All right, yes. I will be talking about function fields. If you don't know what that is, I will tell you what that is as part of it. So yeah, I'm Christelle. You can call me Christelle. And I will be assigning you homework. I will be writing exercises, sending them every day to be uploaded on the website. And my plan for the week is to go back to my hotel in the afternoon to sleep and then be back in the evening sessions. So if you have any questions or you want to talk about what I'm covering in this course, I should be at the evening sessions for at least like a couple hours, like 7 p.m. to 9 p.m. So we can talk at that time. Or I'll be here in the mornings too. So if you catch me like during a break and lunch, you can also talk to me then. So don't think if I'm not there in the afternoon that I've disappeared forever and will never come back. I will. Okay. I've prepared lecture 1, obviously, and 3. And I'm not sure what will happen in 2. I need to figure out what needs to happen in 2 for 3 to happen. So the plan is today, and I'm just going to practice seeing how big this is. So lecture 1, that's pretty good. Okay, will be all about non-Archimedean fields. Okay, FLDS is for fields because I was running out of space. And then 2 will be, I'm going to call it for now, odds and ends. Various things we need to know about function fields to continue with our lives. And then lecture 3, I will introduce the Carlitz module, which is a really good friend of mine and soon to be yours. And then finally, in lecture 4, I'll be able to talk about Drinfeld modules. There will be a big payoff for all our work, and I will focus on the rank 2 case, although I will try to gesture at higher rank whenever I can, and it doesn't make our lives too difficult. And the way I kind of envision the series is that it's going to get progressively harder as we go. So today, I hope that everybody can follow like pretty much everything and look at all the exercises and get something from all of them. And then, by the time we get to lecture 4, I'll be proving fewer and fewer things and asking you to take more and more on faith. We'll have developed a trust bond, so you'll hopefully believe me. So that's the plan. Okay, and now I'm supposed to flip these, so just give me 5-10 seconds. Okay, no, this isn't so bad. Great. So for today's lecture, I was really indebted to Gouvea's book on p-adic numbers. Even though this lecture is not about p-adic numbers at all, there's a lot of background on non-Archimedean fields there, and it's a great book. If you're not careful, like me, you might find yourself at 11 p.m. just reading through further chapters for fun. So only take this out of the library if you have some time. But it's really a wonderful book. And some of the exercises I give are these exercises, but I just made them about function fields instead of p-adic numbers. So I must properly attribute. So recommended. Okay. What are we going to talk about? Well, I'm going to start with the Archimedean property so that you know what non-Archimedean means. So the Archimedean property. I will say one thing that I disagree with the book is that Gouvea spells Archimedean with an I think, here. And we're not doing that here. I mean, you're welcome to do what you want in the comfort of your home, but don't show me that. Okay, so I'm going to let K be a field with an absolute value. And if you're not sure exactly what I mean, I will give the definition. But for now, just think of the absolute value. And I'll write it with 2 bars and like a dot. The dot is where like the number goes, where that you would take the absolute value of. Okay, then K is Archimedean. or has the Archimedean property, but this is shorter to write, if for any x that's not 0, and x is in the field, and any y, again in the field, okay, there is a positive integer little n such that, okay, so I can take, so what I'm thinking, and I didn't write it down, but like in your heart, you should think of x like as maybe like no matter how small. Right? Maybe I try to be really tricky and pick like a really small x, and y maybe try to be like a really big y, no matter how large. Right? But I can always pick an integer n such that if I take x and I add it to itself and I add it to itself and I add it to itself n times, maybe many times, okay, and I take the absolute value of that, that's bigger than the absolute value of y. Right? So even if I take like some tiny, tiny little x and really, really big y, I can just take my tiny little x and add it to itself like maybe 1,000,000 times, maybe 10 million times, I don't care, but I can add it to itself enough times to get bigger than y. So the way you can think about it is like there's no x that's infinitely small, right? That would have to like add to itself maybe infinitely many times, which I can't do. Okay, or there's no y that's infinitely large, so like too big to be overtaken by an x. And you know, maybe you're like, duh, okay, because a good example of an Archimedean field is, for example, the real numbers with the usual absolute value, right? Even if you start with like x is 1 over 1 million and y is 1 million, you should have to add 1 over 1 million to itself, probably 1,000,000 times squared to be 1 million. Okay, that I didn't work that out, so if that's not true, don't like quote me on this. Okay, and so that's how life is usually. And today we are here to talk about not that, when this does not happen. Okay, so, and we'll have one particular non-example in mind that is my goal for the rest of the lecture, but today I'll talk about non-Archimedean fields in general, but still introduce you to our non-example. So our non-example. And by that I mean it is an example of a non-Archimedean field. And I was explaining to someone last night, I was like, well, there's really two kinds of field, the Archimedean ones and the non-Archimedean ones. And it's not a very deep statement, but that's how it is. So I'm just setting up my notation. FQ be the finite field with Q elements. And here P is going to be a prime, and Q is going to be P to the R for some integer R greater than or equal to 1, right? There's only finite fields with a number of elements that's a prime power. So here P will be my prime, Q would be the power of that prime. And then I'm going to kiss it. So that's a field, but that's not the field. Okay, I'm going to consider FQ brackets T, which I will say like this very fast. The polynomial ring in T over FQ. So just, polynomials, like an element of this would be like T squared plus 5T, maybe, or something like that, if 5 is an FQ. So that's not a field, so it's not the field. The field is going to be FQ round brackets T which is, right, all ratios A of t divided B of t, which is that A and B are polynomials. And of course, B is non-zero. Okay, weird stuff's going to happen, but we're not going to divide by 0. Okay, so that's our field. I was going to say something about finite fields, but I think Eric is covering that in his course, so I won't. I just want to say one thing that was confusing, and maybe I'm admitting to being a very kind of basic person, but just one note about finite fields if you're just starting with them, right? If R is 1, so I'm talking about FP, right? The field with a prime number of elements, that is Z mod PZ. So that's a ring you might know from your life before. So the usual like clock, arithmetic, very easy, very nice, right? But if R is not 1, right, FP to the R is not Z mod P to the RZ. I don't know why for me that took a long time. Okay, this one on this side, that's not a field. It has 0 divisors. So don't. And if you're like, but then how do I think about this? Well, just think about that. It doesn't, none of what I'm going to say really depends on P being a power of a prime. So just think of a field with a prime number of elements. But then do go play with fields with more elements because it's satisfying to get good at that. Okay, so if we go back, right, this flip book is fun. So I have a field, I got this far. So I need an absolute value, right? And I talked about things being small and large. And my field has, maybe polynomials in them. I mean, ratios of polynomials, but let's think of polynomials because they're a little bit easier. So we need an absolute value on FQ brackets, round brackets T. And so, okay, so first, what do I mean by an absolute value? So let me give you the definition, because I was going to say, maybe you're thinking of the degree of a polynomial as a size, but then I was going to tell you, no, that's not an absolute value, and then I realized I didn't tell you what an absolute value was, so how could you agree with me that it's not an absolute value? So let's first tell you what an absolute value is. I should follow my notes. Okay, so let K be a field. An absolute value. So I'm going to start abbreviating an absolute value on K is a function. And it does what you would think it does. Okay, so it goes from K. I'm going to talk about real absolute values that take values in the real, positive real numbers. You can get a lot fancier than this. Like I should have like a linearly ordered group or something. But we're going to keep it simple and just assume that things have sizes that are positive real numbers. Actually, non-negative, because I'm about to say one element that has absolute value 0. So take that to include 0. Okay, so such that, 1, the absolute value of x is 0 if and only if x is 0. So there is one element that's allowed to have size 0, and that's 0. 2, the absolute value of x times y is the absolute value of x times the absolute value of y. Okay, so on this side I have multiplication in my field. On this side I have multiplication in the positive real numbers. And then 3, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Okay, and here this is for all xy in my field. This is for all xy in my field. And this last property you might have seen called the triangle inequality. Okay, because if you have a triangle and you do, like, you walk along one side and then the other side, that should be longer than walking along the third side, if you visualize it as vectors. Yeah?
Is this the same thing as a norm?
I think so.
Oh.
Yeah. The question was, is this the same thing as a norm? And I want to say yes. I think like on a vector space, you might call it a norm, and like on a field, you would call it like an absolute value or something like that. I'm going to call it an absolute value, and it's going to have these properties. Okay, so we need one of these for this person field. And like I said, right, one idea might be to do the degree. Okay, so for an absolute value on FQ round bracket T, maybe take, the absolute value of A to be the degree of A if A is a polynomial, and the absolute value of A over B to be the degree of A minus the degree of B if A over B is in my field. Right? That seems like a reasonable notion of size. If we're reasonable people, like T cubed should be bigger than T, right? And T cubed should have like size 3 or something like that. Okay, but that will not do for kind of a silly I mean, it's not silly, right? It's math. We made a definition. It doesn't work. It doesn't work. There's no judgment, but it doesn't work, right? Because if I have A and B still two polynomials, okay, so I'm going to stick to polynomials because one counterexample is enough, right? The degree of A times B is equal to the degree of A plus the degree of B, right? When I multiply polynomials, their degrees add up. But what I wanted was that when I multiply polynomials, their degrees multiply, and that is too bad. Thankfully, there's always a trick. When you have addition, when you want multiplication, you can just exponentiate. When you have multiplication, you want addition, you can just take the log. So it's not that bad. But this happens enough that there's like a whole other thing that we call this, that I'm going to introduce for you, to you, so that you know the words, because I guess I'm trying to teach you stuff. So this happens enough that we have a word for this. How am I doing for time? Oh, pretty good. Okay, so other definition, like K, be a field. It's always going to be a field. Okay, a valuation on K is a function. Okay, I'm going to call it V because I'm super creative. To R union infinity. And again, I wouldn't need to pick R here. People get very much more creative than me on this, but we're going to focus on the case where the valuation takes a real value or possibly infinity. Okay, such that 1, the valuation of x is infinite if and only if x is equal to 0. So one person is allowed to be infinite to take that value, and that is 0. 2, the valuation of x times y, okay, so that's a times, is equal to the valuation of x plus the valuation of y for all x, y. So this is, like, I just fixed my problem, right? If only I had said that, if only I had said that I wanted that the degree, right, would be a sum, then I would win. And so that's why I'm doing that now, right? So that will be good. And then the valuation of x plus y, that's a little weird, but I want that to be greater than or equal to the minimum of the valuation of x and the valuation of y for all x, y in K. And I want equality here if the valuation of x is not equal to the valuation of y. Okay. Just drink this in for a minute. Right. So this last condition is maybe the one that's a little weird, but it's not that weird, hopefully, after we think about it for a bit. So for us, we will let the valuation of a to be minus the degree of a when a is a polynomial. And then when I have a ratio a over b, then that will be the degree of b minus the degree of a. Again, a, b are polynomials. So that's how I extend to the fraction field. And of course, the valuation of the zero polynomial is infinity. That's enforced by the definition. Okay, so let's check that this is a valuation. Right, I said that I would call it a valuation, so I should, show my receipts. Well, if I set the valuation of 0 to be infinite, then if I have the valuation of a over b, right, to be also infinite, then it means that somehow I had the degree of b minus the degree of a was infinite. And here I'm not really thinking, sorry, I'm getting myself confused between plus and minus infinity, and I'm just going to try to not think about that. I'm going to think of the real numbers, and there's infinity at both ends, and that's just like infinity. So I'm not going to worry about plus or minus infinity. But anyway, right, if these are both finite polynomials that are not 0, then this is some finite number, so I'm not getting infinity out of it. And the only way that I can get infinity is if a were 0, and b is not allowed to be 0. So anyway, so that's the only way, right? And if a is 0, b can be whatever it wants. 0 over b is 0. So, that implies a is 0. So a over b is 0. Okay, that's not like the tough part. Then, right, I can check that the valuation of a divided by b times c divided by d, right, blah, 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 that I get the sum in the end. And I'm actually going to leave this as an exercise. It's like a fun extension of what I've done before with degrees, right? You can kind of, like write this as one fraction and then write it out as the degree and then play and play and play. And then the last one, right, is the weird minimum one. So that's the one I want to focus on. That's why I'm kind of skipping through the less interesting stuff. Okay, so I'm going to do 3 only for a, b, some polynomials. I'm going to leave the case of A over B and C over D field elements. To you, gentle listeners, just because it gets annoying, I'm going to have to add polynomials you don't want me seeing added in fractions live. Okay, but so, right, if I have two polynomials A and B and I add them, by definition, I said that I wanted that to be minus the degree of A plus B, right? So that's my definition. And then, okay, so this minus is just going to mess me up. So I'm going to ignore it for a second. Okay, so I'm just going to start over here with the degree of A plus B so we can talk about something that makes sense. Okay, so, okay, think in your heart of two polynomials and you're adding them together. What's going to happen to the degree? Say you have, like, this is degree 3 and that's degree 2. You add them together, the sum is going to be degree 3. So you might think, right, that you're going to get the maximum of the degree of A and the degree of B, right, the bigger one. But what if this one was degree 3 starting with like t cubed, and this one was the degree 3 starting with minus t cubed, and you would end up with something smaller. So actually this is why we have the inequality here. When you add two polynomials, the degree could drop if actually you were subtracting. Or even, I mean, here I'm working over a finite field, so if I was like over F3, I could have 2t squared and 1t cubed. I'm not even subtracting. But anyway, that's not the point, right? So this is what's going on here. And you see, though, the equality, if the degree of A is not equal to degree of B, right? So if they're different degrees, then that cancellation can't happen. I can't have my t cubed and my t cubed canceling each other out. So if the degrees are different, actually I will always hit the max degree there. So that explains this condition, I hope, you know, in some weird way. I mean, in some way that makes sense. And now it's just a matter of like, okay, what does the negative do, right? Like how does that somehow become a minimum and all that? Well, that's just like doing some arithmetic, right? So if I multiply both sides by negative, okay, that flips the inequality. So that's minus the max of degree of A, degree of B. And now I had to draw like a little chart for myself to get to the min and the minus, to get the minus inside, right? So that's literally what's on my notes here. That's 0. And I was like, okay, say the degree of A, right, is bigger and the degree of B is smaller. Then the degree of the minus the degree of A, right, would be down here, and minus the degree of B would be there. And so if I'm, right, like this is the max and I'm taking the minus, so I'm taking this point out. I have so many colors, right? So this is like my max. So this is like the minus of the max. So then what I can think is that the minus of the max, right, this is actually the min of the minuses. Right? Like when I flip them, the max becomes on the bottom. So now I want the smaller one of the two. Okay, and so that finishes my thing. That's the valuation of A plus B. And that's greater than or equal to the min of the valuation of A and the valuation of B, which is exactly what the weird third condition was. So it's just, I mean, I don't know historically how this happened, but if they were thinking about polynomials and they wanted to write down what happened with degrees of polynomials, that's what they would have written down, because that's what happens. Okay, and the equality is explained by like the cancellation. Okay, well, I write much bigger than we expected, so I'll just start feeding paper underneath it. And won't have my nice flip book. Okay. And then what's the connection? So that was like big to do about valuations, but I kind of sold you absolute values. So right now maybe you're disappointed, but definition on this field FQ round brackets T, we will define the absolute value of x to be q to the minus v of x, where v is that valuation from before, q is the size of the field. Okay, I could have picked any constant, but I have any constant greater than 1. But I have a really good constant there, and so that's the one that I pick. Okay, so just to, nail this in, because we're now several pages in, the absolute value of a over b is going to be q to the degree of a minus the degree of b. Okay, because if you remember, my valuation kind of did like the degree of b minus the degree of a, and then like I'm minusing in that anyway. Okay, and then I'm going to leave it as an exercise. Okay, check that this is an absolute value. Okay, so I told you like 3 things that should be true about absolute values, and so you should check that those are true about this one. And the exponentiation, right, is going to make our plus problem become a multiplication, so this much will be good. Okay, so if we flip back, I started out with the Archimedean property, and I was like, this is not about that. So now, what should I do? I should show you that this is not an Archimedean absolute value proposition. This absolute value is not Archimedean. You have to pick. Either you say non-Archimedean and then you do get to put a dash between them, or you say not Archimedean and you're just negating an adjective and you can't put a dash. I will usually mess that up. Okay? And, well, if you remember way back when, the definition of Archimedean, it's a for all statement, right? I have like for all x and any y, blah, blah. So it's really easy to show that you fail a for all. You just have to fail once. So pick almost anything and you will win. Okay, so I can pick my little polynomial to be, say, t, and my big polynomial to be y, right? And then no matter how many times, right, I add t to itself, right, any n times, that'll still be a degree 1 polynomial. Like polynomials cannot escape their degree by addition. They're stuck. So that will always have absolute value q, right, q to the degree, so 1. And that will always be less than the absolute value of t squared, which is q squared. So I will never, right, polynomials by addition don't get any bigger. Yep.
Does this mean that there's no absolute value we can put on this field to make it Archimedean?
You know, that's a question that I found in this book and that I thought about for a few minutes, and I couldn't come up with one, but I didn't think of Googling it. So all the absolute values that I know on FQ brackets C are all non-Archimedean, but I'm not saying that there's not some more wonderful way.
Wouldn't you have to have characteristic 0?
Sorry?
I think it would be necessary to have characteristic 0.
To have an Archimedean okay, so it's possible that characteristic 0 is necessary for an Archimedean absolute value. Exercise. Google this and report back. Or prove it if you're more advanced in the exercises that I'm giving. All right, so I have 6 more minutes. So the way that I've been talking about this is with this addition, which is not in my mind, the best way to talk about this. So I will state, but not prove, a very nice, what I think is a nice way to think of non-Archimedean values, absolute values, proposition. An absolute value is non-Archimedean if and only if it satisfies instead of the triangle inequality. So way back when I defined an absolute value, there was like something about 0 being special, and then something about multiplication being good, and then the triangle inequality. I was like, triangles, right? So it will satisfy the triangle inequality, but instead of that, something even stronger. Okay, so it's not really like an instead, like it doesn't satisfy that, but it's like better, right? Like instead of one muffin, you got 2 muffins, and they're chocolate. Okay? Instead of the triangle inequality, the stronger ultrametric. Oh, and there is a great quote in this book about the ultrametric inequality, which I don't remember. But anyway, get the book, read the quote. Okay? Inequality. That the absolute value of x plus y, right before I was like, oh, is this equal to the absolute value of x plus the absolute value of y? That's so weak. That's so weak. That's less than or equal to the maximum of the absolute value of x and the absolute value of y. So that's, this is a lot smaller, right? So this is a lot better because like I'm bounding above by something smaller. So instead of being like, oh, I take the absolute value of x and the absolute value of y and I add them together and then you can't be bigger than that. This is like, no, you take like the larger one of these two and it's not bigger than that. Okay. And then again, I have with equality, if the absolute value of x is not equal to the absolute value of y. And the explanation for this equality thing is the same kind of thing with the degree, right? If I want the size to be strictly smaller than the bigger one of the two, there has to be some cancellation, and for them to cancel in some way, they have to be the same size. If they're not the same size, then the bigger one is going to stay bigger, and the littler one is not going to be able to cancel it. So I'll get that the size of the sum is exactly the size of the bigger one, just like for degrees. Okay, so the proof of this is not, I mean, one direction is not so hard. Which one? Yeah, if you have the ultrametric, I mean, I'm not going to prove it, like proof idea, right? Ultrametric implies non-Archimedean is not bad. So I recommend that you think about that. Okay, the other side is like a little tricky, and you do, okay, other implication is tricky, but I mean trickier, like none of this is as difficult as other stuff you'll see this week. But I encourage you to think about it and or look it up. I looked it up, I'm going to be honest with you. I looked it up and it was a very satisfying argument. Okay, but I just want to add, I have, I think, 5 minutes. I don't know. It feels like this clock's not moving in the back, so that means I can stay here forever, right? I just want to end with some surprising facts about non-Archimedean fields because we should have some fun. Okay, so proposition in a non-Archimedean field, right? So, and what do I mean by a non-Archimedean field? I mean like a field equipped with a non-Archimedean absolute value. Okay. Every triangle is isosceles. No more fighting. Yeah. Okay, so what do I mean? I mean that if I have, 3 points, either the distance between x and y is equal to the distance between x and z, or the distance between x and y is equal to the distance between y and z, or the distance between, what's the last one, y and z, is equal to the distance between x and z. One of these has to be true. Has to happen. So already you should start thinking that this is going to get strange, right? Or if I define, okay, so the ball with center A and radius R to be all of the points in my field such that the distance between x and A is strictly less than R. Okay, R is some, positive real number. So the usual ball that you remember from having balls. Okay, then these balls are weird too. Right, so definition this is a proposition in a non-Archimedean field, right? 1, if B belongs to the ball with center A and radius R, then if I make the ball with center B and radius R, which you would think would be a whole other ball, possibly next to the ball that you had, you would be wrong. That is just the same ball. So every point is the center. Every point in the circle is the center of the circle. Every point in the circle is in the center. No more fighting. Say I have 2 balls, possibly different. Right? I have the ball centered at A with some radius and the ball centered at B with some different radius. And I assume that they intersect in some way, right? So you're imagining like a Venn diagram, maybe, because you're wrong and you're thinking in the Archimedean case. This implies that either one ball is in the other ball or the other ball is in the first ball. Balls can only be disjoint or completely inside each other. Okay, so this is weird. And then the last one, if you know some topology, the open, let the record show that I had air quotes around open, okay, is both open and closed. In the topology given by the distance metric, so x minus y. Okay, so if you're like, what's a metric? What's a topology? You don't need to do this exercise. But you should prove all these because they're super fun. And they all use the ultrametric inequality. Okay, and then, still 2 minutes. I will tell you, so maybe these you thought were good or bad. I think it could go either way. But I will tell you one thing that is definitely good. And I won't have time to set up what a completion is. So you'll hopefully pardon a little bit of hand waviness. I'll do completions tomorrow. Thankfully, we have so many days together. Okay, but proposition let K be a complete non-Archimedean field. Okay, so to me, this is what makes it all worth it. This series converges. And now if you remember calculus, like I would have to pull out like a root test or a ratio test or like alternating series or something awful like that. Okay, but in my awesome non-Archimedean world, this is true if and only if the limit of the terms is 0. Actually, the absolute value of the terms is 0. So we will rely on this a lot to make everything easy when we start defining functions next time. We'll be like, when it goes to 0, we win, which you cannot do in calculus. So all of your dreams and more will be realized next time when our life is a lot easier. Thank you. Sorry. But then they wouldn't go to 0. Yeah.
So, Christelle, the video recording of your lecture will have a little screen of video of you.
Oh, so I don't have to say. Phew, that makes me feel a lot better. Now I'll just gesture all the proofs from now on. There's no more writing or words. Yes?
On the question about whether norms and absolute values are the same, I think they're distinct in the sense that you would have to define an absolute value first before defining a norm, because when you pull out a scalar from a norm, you're multiplying by the absolute value
of the thing. Yeah, that's why I was like, I feel like norms are more for vector spaces, and then you would use the absolute value on your field to talk about that. But at the same time, right, if you're thinking of the field as a vector space of like dimension 1 over itself, then probably the norm and the absolute value are exactly the same thing. So it's not wrong. I mean, it's not right, but it's not wrong to think of them as the same. They're the same idea, right? Oh, okay. So I'll go front to back.
Does every non-Archimedean absolute value comes from evaluation?
Yes, that's an exercise. So you're gonna have fun tonight.
I was trying to. There is no Strauss-Hughes theorem for like function fields, so they're all non-Archimedean.
They are all non-Archimedean, right? So we can't be tricky. Field is tricky. Yes.
Does limit xn equals 0 not imply a limit absolute value of them equals 0?
Maybe that's true, and maybe I pulled an audible. I didn't have the absolute value in my notes, and then I was like, I want the absolute value there. So I would have to think about it when I'm not like standing in front of 100 of you. And there was a question in the back, so I'm not forgetting any of the people that ever raised their hands. That's a lie. I will forget. Okay, well, maybe I answered it already, or you have to pee and you're like, please let us go. I think that's it.
Thanks, Christelle, again.